Hi, I'm Tony Heiser with KEB America. I'm the Business Development Manager for Commercial Electric and Hybrid Vehicle Applications. Today, I'd like to talk about electrifying auxiliaries in commercial electric vehicles, and I'll give an overview of KEB as a company, as well as introduce the KEB T6 auxiliary inverter system.
As an agenda of topics, I would like to start by providing a company overview of KEB. Next, I'd like to discuss the topic of electrifying auxiliaries. What are auxiliaries? What do we want to electrify? And why do we want to electrify them? Then lastly, I'd like to introduce and discuss the KEB T6 auxiliary inverter system. I will explain the design concept, then discuss the main topics of system connections, motor control and inverter stages, electromagnetic compatibility, or EMC, the role of the embedded controller and some of the unique opportunities it provides, and finally, the tools for programming and support. To start, KEB is a leading global manufacturer of industrial control and automation products. The company was founded in 1972 and remains a privately held, family-owned company, and today has more than 1,500 employees worldwide. KEB Automation KG is headquartered in Barntrup, Germany. Additional production and sales facility include KEB America based outside of Minneapolis, Minnesota, as well as KEB Power Transmission Technology based in Shanghai, and KEB Antriebstechnik based in Schneeberg, Germany. Globally, the company also consists of subsidiary sales offices throughout Europe, as well as representative offices and distributors worldwide. KEB's products consist of a vertically integrated portfolio of control and automation components ranging from the HMI touchscreen, where the user gives the machine a command to operate, down to the motor shaft, which performs the actual work, including most of the components in between. The primary product groups include embedded controllers, inverters for AC motor control, AC motors, both induction and permanent magnet servo motors, gearing products and integral gear motors, electromechanical clutches and brakes, and lastly, other specialized industry-specific products, such as for eMobility. KEB's market approach is to focus on specific industries and applications. Here, we work with customers to develop industry-specific solutions and gain experience to become experts in these fields. Some of the markets and applications KEB focuses on are eMobility, compressors, pumps, and fans, high-speed machinery, including turbo compressors and turbo blowers, and elevators, hoisting equipment, and cranes. There are many other applications where KEB has a strong presence, but I found these to be perhaps the most relevant, potentially pertaining to commercial vehicle applications and auxiliaries. So, circling back to the primary topic of discussion, let's start by defining exactly what are auxiliaries. As a bit of background, electric vehicles namely replace a constant running combustion engine with an electric motor for power on demand. Generally, this primarily pertains to the traction power, that is, making the wheel spin when you press the pedal, thus power on demand. But the combustion engine also plays another role. It drives a serpentine belt, which mechanically powers a number of smaller secondary or auxiliary loads. These auxiliary loads in consumer automotive vehicles are recognizably the power steering pump, AC compressor, and water coolant pump. And for commercial vehicles, there are many other additional auxiliary types. So, without a constantly running engine to power these loads when needed, there's the opportunity to electrify them by powering them with electric motors as well. What auxiliaries do we want to electrify? Steering pumps, air compressors for brake and suspension systems, as well as air conditioning, HVAC, and transport refrigeration reefer units, hydraulic system pumps, coolant pumps, fans, fuel cell balance of plant components, which include the turbo compressor, hydrogen recirculation blower, and coolant pump, electric PTO, and there are many other items that can be driven with direct drive or geared motors. Well, I've already made the case for the need to electrify the auxiliaries when the engine is replaced with the motor, but there are additional benefits to electrifying auxiliaries as well, thus also making the case for hybrid solutions when the engine must be retained. First off is power on demand. That is, the ability to operate a device whenever it's needed. With power on demand, a device can operate independent of whether the rest of the vehicle is in operation or not. A good example here is stationary working equipment such as a bucket lift truck. In this case, by electrifying the hydraulic pump which operates the lift, the operator could use the bucket lift without having to keep the engine idling. This also allows for quiet operation within residential neighborhoods. Another benefit of electrifying auxiliaries is better performance. Auxiliary operation independent of engine speed can unlock its potential. There is no longer the conflict of lacking power during idle or low engine speed. In some instances, the needs of an auxiliary are at odds with the engine's operation. This can often be the case in hydraulically powered equipment as well as PTO-driven equipment. As an example, a bulldozer's engine RPM may drop while driving into a pile at low speed, which is in contrast to the higher engine speed needed for the hydraulic pump to lift the loaded bucket. On the other hand, utilizing an electrically driven hydraulic pump would have the pressure primed and ready. This is also another example of power on demand. Again, it's power when it's needed and independent of other vehicle systems. This also demonstrates the increased dynamic response to loads. Another example of increased dynamic performance is in the case of performing low-speed steering maneuvers. Here, an electrified power steering system can provide peak power on demand in this situation, as well as quick dynamic response to the high-pressure steering force changes. Next on this list is increased efficiency. Compared with mechanically driven systems, electrically motorized systems are generally going to be more efficient from a power in, power out standpoint. That is, after considering all of the losses between power source and actual work being done. Mechanical linkages such as transmissions, gears, belts, and pulleys between engine and auxiliary can amount to large losses. On the other hand, an electric motor generally operates between 90 to 95% efficiency depending on load and speed. Here, an electromechanical system can even be tuned to the motor's most efficient operating point at the auxiliary's nominal operation. Another point in regards to efficiency is that engine-driven auxiliaries can be parasitic loads to the engine itself, especially when not in use. By electrifying these loads, there is the benefit for hybrid applications whereby decoupling these loads from the engine can increase fuel efficiency or potentially allow for a reduced engine size. Then, there's also the benefit of quiet operation. I don't know whether a diesel truck has ever snuck up on anybody, but there is a safety concern with electric cars that people won't hear them coming. Electric motors are definitely quiet. On some of the power steering applications we've worked with, users have noted that the quiet operation has been one of the primary benefits for them. Another opportunity with electrification is the potential to eliminate hazardous chemicals, namely hydraulic fluid. An industry term for this is hydraulic replacement. That is, replacing components driven by hydraulic systems and directly driving them with electric motors. A brief example would be a street sweeper application where the hydraulic brush motors instead utilize electric motors either driven directly or through a gearbox. And lastly, electrifying auxiliaries also plays a role in the overall goal of lowering emissions. So, in what types of vehicles do we want to electrify the auxiliaries? First, there are trucks, from small delivery vans to heavy-duty Class 8 semis. There's also municipal equipment such as refuse trucks and street sweepers. Then, there are bus applications, which include transit and coach buses, as well as school buses. Next, there are fuel cell balance of plant applications. Granted, not a vehicle type itself, is a system which could potentially be used in any one of these vehicle types. And lastly, there's also off-highway machinery. This includes agricultural machinery such as tractors, as well as the implements. Then there is also off-highway construction equipment and mining vehicles. They all have multiple auxiliaries which can be electrified, and KEB solution is the T6 auxiliary inverter, a scalable and modular system solution. So what do we mean by a system solution? Here I've divided up into main topics: system connections, motor controller inverter stages, EMC solutions, embedded control, and tools and support. Let me start with the design concept of a system solution. Starting with a single inverter stage, there are the central system connections. These include one high voltage DC input, one low voltage harness connection, including the CAN communications, and one set of liquid cooling connections. Moving on, there is the motor control or inverter output stage. Here, the system can be scaled to support multiple independent motor control outputs, up to 6 total within the system. Next are EMC solutions. This includes integrated DC common mode chokes for each inverter stage. Then, there is an onboard embedded controller for system management and pre-programmed solutions for easy setup. And finally, there are the system software programming tools for setup, as well as technical support. To put the system scalability into context, let's take the example of a waste truck application. Here, the application may start out as a single inverter stage for electrifying the steering pump. The system could then be scaled to 2 inverter outputs to include an air compressor for the braking system. The system could continue to scale to include the hydraulic pump for the body hydraulics. And finally, the system is scaled to 6 inverter stages. Here, I provide an example of a hydraulic replacement solution where the body hydraulic system is replaced with motors for the bin grabber and lifter, as well as the hopper compactor and ejector. Why a system solution? There are many potential benefits to consider. First, a system solution provides a flexible and expandable platform to easily support multiple vehicle types and configurations. Such is the case where you have a chassis with different types of body equipment. Whereas the power steering and air compressor may stay the same for the chassis, the body equipment may change, or there may be optional external equipment such as a transport refrigeration unit or electrically driven PTO devices which may be integrated into the system. The system approach easily supports all combinations of chassis, body, and external equipment. In the picture is an example which combines two separate systems into one, semi-tractor and a TRU. From a cost standpoint, a system solution reduces redundant components compared with multiple distributed systems. This includes reduced high voltage DC cabling, DC fusing, low voltage wiring harnesses, and liquid coolant plumbing. Not only does the reduced number of components reduce costs, but also reduces system complexity. Also in terms of costs, as the number of inverter output stages in a system is scaled, the marginal cost to add each additional stage continues to go down. That is, a 3-output system does not cost 3 times a single output system. This makes larger, multi-axis systems particularly attractive from a pricing standpoint, even more so when you consider the reduced amount of cabling and other components previously mentioned. Another benefit of a system solution is a uniform programming environment. Having a different inverter brand for each auxiliary, or in some cases different hardware or software based on motor type, will mean a learning curve for each. Furthermore, different auxiliaries may have different ways to set up the CAN communications, all of which may slow down the development process. With the uniform programming environment, once you've tackled one axis, the rest should be as easy as rinse and repeat. Likewise, from a CAN communication standpoint, a system solution can consolidate multiple inverter nodes into a single CAN node ID with separate PGNs for each output stage. Overall, this can help simplify the setup and clean up some of the traffic on the vehicle CAN bus. And lastly, another benefit to a multi-axis system solution is that it can provide additional mounting options. In the case of the T6 auxiliary inverter, the unit is IP67 rated and can be mounted on the chassis. Here, orientation of the unit provides flexibility as well. And I should note that the T6 system supports motor cable lengths up to 30 meters. This is enabled by our EMC Solutions, and not all other inverter manufacturers have this option. This further allows for the T6 system to be located somewhere convenient, rather than having to be co-located with the auxiliary and taking up valuable space under the hood where some of these auxiliaries are located. Coming back to the point of reducing system components, I want to exemplify this by showing a comparison of a distributed system with separate inverters for each auxiliary with a consolidated system solution. Here, you can see with a distributed system that each device has its own DC cable and fuse, there are multiple plumbing connections for liquid cooling, and each device has its own CAN node ID on the network. Now, compare this to a consolidated system solution. Not only are redundant components eliminated, but the system layout is simplified as well. Also in regards to the design concept, I wanted to cover the topic of design for vehicles. To start off, we have approvals for the product, which include CE and E1 markings, with the E mark being required in Europe for sale of components to the transport sector. T6 units are also designed using automotive qualified components and are produced meeting automotive quality standards as certified by the KBA, which is the German Federal Transport Authority. In terms of the mechanical specifications for which the T6 was designed for vehicles, the ambient operating conditions for which the units are tested is -40 to +70 degrees Celsius. The units meet shock and vibration standards according to ISO 16750-3 Code L. The units have environmental protection ratings of IP67 or IP6K9K, depending on whether you're referring to the DIN or ISO standards. In either case, you have an enclosed unit with protection against water. The units are liquid cooled using a water to glycol mix of 45 to 55 with a max coolant temperature of 65 degrees Celsius, a minimum flow of 5 liters per minute, and a maximum pressure of 2 bar. For motor cables, lengths of up to 30 meters have been qualified. And in terms of mounting, several orientations are supported. From an electrical standpoint, the supported voltage range is 200 to 820 volts DC with a nominal rating of 565 volts DC. Also supported is a high voltage interlock loop. The output power rating of the inverter modules are 7.5, 15, and 30 kilowatts, and the respective current ratings are shown. I'll circle back to this in more detail later. And from a system standpoint, the continuous electrical power rating is 60 kilowatts continuous with 90 kilowatt peak capacity for 30 seconds, or in terms of DC current, 120 amps DC continuous with 180 amp peak for 60 seconds. I'll come back to this later as well. From the low voltage side, supply and signal voltages between 9 and 32 volts DC are supported. The units are tested in accordance to EMC standards for CE, E1, which includes ECR10 and CISPR25, and lastly, EN 61800-3. And from a communication standpoint, CAN J1939 protocol is supported, including diagnostic trouble code messages DM1 through DM4, as well as CAN Open is supported. Getting back to the main system solution topics, I'll start by discussing the system connections. Each T6 system starts as a single inverter with a main connection unit and an embedded controller. The system connections include the high voltage DC input, a diagnostics port, the low voltage harness connection, which includes the low voltage power supply, CAN ports, the KL15 or enable input, and the high voltage interlock loop control connections, the liquid cooling connections, and last but not least, the earth ground connection. And although it's not a central connection, I'll talk about the connectors for the inverter output or the motor connections as well. These connections are M23 or M40 connectors depending on the power module size and are speed-con locking connectors for quick and easy connection. These connections are 3-wire UVW motor phases with ground and temperature sensor connections. The connector socket on the T6 itself is horizontally rotatable up to 310 degrees, and the maximum qualified cable length is 30 meters. From the embedded controller side, this is an internal PLC, which acts as a central CAN gateway for the inverter stages, as well as a central system management. More on this later though. The next main topic I'd like to discuss is the motor control or inverter stages. Here, I'll break this up into the categories of hardware and software. To start, as I have touched on, the inverter system is scalable from a single inverter output up to 6 independent outputs. People usually ask about dimensions at some point, so I'll show them here. I'll pause for a moment before I scale out the other system lengths. Otherwise, the height and depth remain the same. In regards to the height and depth, there are 2 connector sizes based on the inverter module rating. Thus, I've listed both of these dimensions. And once again, one set of system connections. So far, I've touched on the modular concept, but I haven't described what that means. What it means is that there are power module options for each of the inverter output stages. We give our power module options letter names. The first power module option A is 7.5 kilowatt with a rated output current of 16.5 amps and 150% overload for 60 seconds. The second power module option B is 15 kilowatts with a rated output current of 33 amps, also with 150% overload. And the final power module option C is 30 kilowatts with a rated output current of 60 amps and a 110% overload for 60 seconds. Now to briefly explain that asterisk next to the power rating. The power rating is based on a 565 volt DC nominal supply voltage. Recall, power equals voltage times current. Thus, voltage supplies lower than the nominal rating limit the available output power, whereas the current rating of the transistors remains the same regardless. In this regard, we always size applications based on the motor rated current rather than the motor power. For example, for a given horsepower, a 230 volt AC motor will generally have a rated current that is twice that of a 460 volt AC rated motor. So this is something to be aware of in general. Again, each output within a system can have any of the power module options. They can be mixed and matched between outputs. As an example, you could have a 4-axis system with 2 30 kilowatt modules, one 15 kilowatt module, and one 7.5 kilowatt module. Given there are 3 module options and up to 6 outputs in a system, there are 83 possible system configurations and all are supported. Now, one area of the electrical specifications that I'd mentioned that I'd come back to is the system input capacity ratings. These are 60 kilowatts continuous and 90 kilowatt peak for 60 seconds, or in terms of current, 120 amps DC continuous or 180 amps peak for 60 seconds. And since power in is equal to power out, we must consider the net power flow. In this case, determining actual system capacity based on the total output capacity ratings is not necessarily a good indicator. It's clear that a system with 6 7.5 kilowatt output modules would be okay from an input capacity standpoint, but in the case of 6 30 kilowatt output modules, it may depend. Here, there may be some considerations. What is the actual motor load of each output? What is the duty cycle of each output? Are the loads producing power, or is power being regenerated back? Taking these into consideration, one can determine the actual net power requirement, and if it exceeds the continuous or peak input capacity ratings, then additional systems may need to be considered. Moving on to the inverter software, the T6 supports all types of AC motors with the same hardware and software platform. This includes induction motors, synchronous permanent magnet and servo motors, including internal permanent magnet or IPM motors, and also synchronous switched reluctance motors. And the following control types are supported: velocity or speed control, torque control, and positioning. And all of these motor control types are supported with sensorless control. So what is sensorless motor control? Sensorless essentially means no encoder feedback. This eliminates the need for a motor encoder and cabling, which reduces costs as well as eliminates potential points of failure. Instead of encoder feedback, sensorless control utilizes a motor model, including the motor characteristics, and utilizes the actual measured motor current and voltage to close the loop. The motor characteristics can be measured by a very easy automated motor characterization learn process, which I'll discuss more later. And the benefits of sensorless control are that it can provide better than closed loop performance, since the internal measurements provide faster response and more precise torque and speed measurements, resulting in dynamic and accurate motor control. Sensorless operation can also yield energy savings in that it can operate the motor more efficiently and with less losses. For example, sensorless uses demand-based power output based on the actual load. By contrast, an open loop system blindly puts out a fixed voltage regardless of the actual power needed. And lastly, sensorless control also allows for automatic and moreover motionless identification of the rotor position for synchronous motors. This process only takes about 150 milliseconds, can even be done if a holding brake is set. Thus truly, no movement is required. Here, I have a sensorless application example with a steering pump, which compares performance and energy consumption between open loop volts-hertz operation versus sensorless closed loop, or SCL. In the table, we have different driving profiles. In the case of driving straight on, you can see that open loop utilizes 9 amps, whereas sensorless uses only 4 amps. This difference can be explained by the fact that the pump is not working particularly hard in this scenario, and in the case of open loop, is simply putting out a fixed power command regardless of the loading situation, whereas the sensorless adjusts accordingly. In the next scenario, the steering is maneuvering a curve. Here you can see that the load and actual currents both rise. In the case of open loop, the actual load is now more in line with the fixed output. The actual load is also confirmed by the sensorless output, which appears to be slightly more efficient. Finally, you have the case of butting up against a curb. In the case of open loop, this results in a very high current of 20 amps, which could trip an overcurrent fault. On the other hand, the dynamic response of sensorless limits the current overshoot to 10 amps. For that matter, it is also possible with sensorless to set thresholds at which to limit the current, such that it is not possible to reach an overcurrent level. The second sensorless example shows the evolution of an application which had initially used a large induction motor for the power steering. With sensorless, the customer was able to switch over to a smaller, lighter, and more efficient permanent magnet motor. Then, by working with the motor manufacturer, an even smaller and lighter unit was developed. Granted, it was also a liquid-cooled motor, but the reduced size was partially enabled through the reduced motor losses and efficient operation offered by the sensorless control. As shown in the corner, the initial induction motor was a 100-pound motor, and the final servo solution was less than 20 pounds and nearly half the length. I should make note, though, that sensorless control has its limitations and is not suitable for all applications. Since the motor model relies on voltage feedback, which is a function of speed, applications involving holding torque at 0 speed or continuous operation at less than 1% of motor rated speed are not suggested. In these cases, encoder feedback should be used and is not currently supported by the T6. Moving on, the next main topic is EMC Solutions. What is EMC? EMC is electromagnetic compatibility. In short, EMC means limiting electrical noise generation and reception to prevent interference or damage between equipment. The result is that EMC considerations mean high operational reliability. Anyone who has dealt with electrical noise and rooting it out after the fact may appreciate what this means and how important it is to take this in consideration from the start. The EMC Solutions incorporated into the T6R integrated common mode DC chokes for each inverter stage, shifted transistor switching on multi-axis systems to reduce electromagnetic interference, and lastly, taking into consideration the shielding and clamping on connectors. In this case, these EMC considerations allow the T6 to support motor cable lengths up to 30 meters. And the next main topic is in regards to the embedded controller. The use of an embedded controller in the inverter is kind of a new concept. So what is the purpose of the embedded controller? Well, it is the main I/O point of connection, provides system management, and is a hub and gateway for CAN communications within the system. And it contains pre-configured software programs, or apps. As the main I/O point of connection, this includes the low voltage wiring harness, which includes the CAN port connections, as well as the input for the KL15 accessory ignition switch, or enable. And lastly, the high voltage interlock loop control connections. From a systems management standpoint, the embedded controller is where the basic CAN settings are configured, including the CAN node IDs and baud rate settings. The embedded controller also transmits global diagnostics, which include DC voltage, total power, heatsink temperature, and overload counter. And lastly, the embedded controller is also where settings for overload management can be configured. That is, in the case of an overload, it is possible to set thresholds and turn off loads according to priority to prevent shutdowns. Now coming back to the last purpose of the embedded controller, what exactly are these so-called apps? In short, they are pre-configured software programs. They act as an interface between the vehicle controller and the inverter to allow for quick setup and easy programming, as well as the possibility of creating custom functionality. But let me provide a little background first to help put this into familiar context before describing a few app examples in further detail. To start, the embedded controller contains CAN-supported hardware and is a CAN controller itself. In fact, the system supports two independent CAN controllers. On the controller hardware, KEB has developed what we call the App Utility Framework, which acts as an operating system. Here, the operating system supports fundamental system configuration, such as CAN node IDs and baud rates. Additionally, it supports application programs. The application programs, or apps, are similar in concept to the programs such as Word or Excel that run on a PC's Windows operating system, or likewise a texting app that runs on a smartphone operating system. On a T6 system, a different app can be selected for each inverter stage. This allows each inverter to run a program best suited for the auxiliary type, or perhaps allow the developer to control or communicate with a particular auxiliary according to their preferences. The function of apps can vary from basic to universal or even custom. In general, apps can contain pre-configured CAN process data and/or pre-configured inverter settings, which allow for easy setup. Apps can provide a means to develop added or customizable functionality. Third-party apps are also supported, which may include programs developed by OEMs or auxiliary manufacturers themselves. As part of the system setup, an application can be selected for each inverter stage from a pool of available applications on the embedded control. Each inverter stage operates independently, so I should note that the same app can be used on multiple inverter stages. As an example, you may have one inverter stage running a simple velocity mode app for a fan. That is, a basic on-off control with one fixed speed and pre-configured acceleration and deceleration ramps. A second inverter stage may run a J1939 process data gateway app where the user may select specific diagnostics to be sent using either Prop A, Prop B, or transport protocol. Lastly, a third inverter stage may utilize a torque speed control app for a steering pump where the controller may send different speed commands and torque limits. As I had mentioned, custom apps can also be created. For an example, an auxiliary manufacturer could create an app with custom functionality. This may include special operating modes like an emergency or low battery mode. It could also include turn-on routines or test functions. It would also be possible to develop control loops, which may take pressure set point commands from the ECU and convert them to motor speed commands, or it may be possible to create custom CAN messages or diagnostics. All these possibilities can open the door for OEMs or auxiliary manufacturers to embed their know-how into the system and create value-added functions and features. Additionally, this means that systems can also be pre-configured for plug-and-play solutions. As a more concrete example, there's the Torque Speed Control app. This app has pre-configured J1939 process data mappings. For the received data, a telegram is set up for the selection of control mode, set point velocity, and the maximum torque. For the transmit data, a diagnostics telegram is pre-configured, and there are 2 additional transmit telegrams which are freely definable. In addition to pre-configured CAN messages, the app also pre-configures the inverter parameters for the corresponding control modes and process data mappings. Thus, the Torque Speed Control app provides for a quick and easy setup for typical functionality and diagnostics. A second example is the CAN J1939 process data gateway. Whereas the Torque Speed Control app was more defined and had pre-configured CAN telegrams, the Gateway app is more open-ended and flexible. Here, there are 3 freely definable transmit and receive telegrams, which the user can populate by selecting the inverter parameters they want to be contained in the telegrams. The app itself then acts as a translator to format the data between the inverter and the CAN network according to the J1939 protocol. The app handles the inverter parameter address mappings as well as the scaling and offsets of those parameters. Additionally, each telegram can be selected to be either Prop B broadcast or Prop A peer-to-peer messages, and the app handles the corresponding telegram formatting. This is also the case for transport protocol of larger telegrams. Lastly, the app also provides flexibility when assigning telegrams to PGNs as well as setting PGN addresses. The result is that there is no need to talk the KEB language. The app allows for easy and flexible setup of the CAN telegrams in terms of the data contained in the messages as well as the format and addressing, all according to the J1939 protocol. And coming to our final main topic is tools and support. First off is KEB's free, easy-to-use software program, CombiVis 6. This program allows the user to connect to the system to change parameters and monitor diagnostics. There are also setup wizards with intuitive interfaces for quick and easy setup. This includes a wizard for an automated motor characteristics learn process. And there's also a virtual oscilloscope, which the user can place diagnostics into the scope channels, run a trace, and evaluate with cursors. This makes for an amazing troubleshooting tool since you can see what's going on, and the scope files can also be saved and sent to others for review. CombiVis also has TeamViewer built in. This is a support tool that enables the user to allow remote access to their desktop for troubleshooting with tech support. And lastly, CombiVis projects and parameter files can be saved. These files can be sent for troubleshooting support or saved and loaded to subsequent systems for quick setup, as well as saved to the T6 device itself, which is useful for production purposes, where customer files can also be loaded at the factory by KEB and the systems will arrive pre-programmed. Now, coming back to the motor characterization process, this is probably one of the top questions I get from customers. That is, have you worked with motor XYZ? How easy is it to pair the motor and inverter? And so forth. Rest assured, the motor learn process is incredibly easy and works for nearly any motor. For us, this concern is generally a non-issue. My personal experience is that I have performed motor learns on literally thousands of different motors without issue. It is an automated process, so the user just needs to follow the steps in the wizard. What's primarily needed is the basic motor nameplate data. This includes the motor rated current, speed, voltage, torque or power depending on the motor type, frequency, and in the case of induction motors, the power factor. After that, it is just a few clicks to start the process, and once the hardware enable command is given, the process will take 3 to 5 minutes, and the learned values will then be stored once complete. That's it. If interested, I have a 5-minute start to finish T6 startup demonstration posted on YouTube, which includes the motor learn process as part of the video. I should also note there's a licensed version of CombiVis called CombiVis Studio. This includes a code assist programming environment for developers who want to create their own custom apps. And finally, in regards to support is our applications engineering team at KEB. We have dedicated eMobility teams, which are regionally based in North America, as well as various locations in Europe for localized support and to address the requirements of the different markets. And we offer assistance at every stage of a project, including design concept, system sizing and selection, startup and commissioning, including on-site support as permitted, series production preparation, and technical and after-sales troubleshooting and support. And in conclusion, KEB's philosophy is that we see customers as partners. So let's work together. What do you want to electrify?